Um, Sorry about it. So I'm going to talk about what do Kepler planets say about planet formation. The reason I changed it, even though I originally intended to talk about dynamics, this is more exciting. And also my collaborator, Yoram Liswe, which I originally applied to give such a talk, but he didn't get a spot, so I thought I need to advertise this. Oh, right. Okay, let me first define what Kepler planet, what I mean by Kepler planet. So I'm sort of using that term Kepler systems or Kepler planets to refer to low mass closing systems. Okay, low mass closing planetary systems. So no giant planets in this talk. And they've been discovered abundantly by the Kepler mission and by the radial velocity surveys. The question is, now you see so many of these planets, what can you learn about planet formation? From my point of view, planet formation is a really hard question, not because physics is hard, but because we don't know the initial condition. We don't know how the disk behave. We don't know how the disk look like, how big it is, how much mass it is, how much junk it has inside it. All this initial condition is not understood. So what do? One philosophy is look at the planet that's actually made and then trace back to see what the initial conditions are. And that's what this talk is about. It's a terrible title. I said, what can we learn about planet formation from Kepler systems? Usually when you see titles like this, the answer is not very much. Let me see if I can convince you otherwise. Oh, sorry. So the first thing I want to put down, the basic tone of this talk is that these systems are incredibly universal. They're not minority systems. These are mainstream planetary systems. We see them in, say, between 15 to probably 50% of the stars. So if there's some scenario you can come up to making this kind of planets, you cannot revoke special situations. Metallicity, higher metallicity, binaries, no binaries. It has to be very universal planet formation. Okay? So that's the philosophical thought. So let me go to two aspects what we can learn about planet formation. This is the two aspects we've been working on the last year. The first thing is, what are these planets made of? What's the interior structure of these planets? Okay. I just listed, before Kepler planets are discovered, what we would expect for the planets nearby to the stars. And the only example we have was terrestrial planets. Those are rocky planets with very little sliver of atmospheres on top. Okay. So that's our prior expectation. And what the Kepler planets are. Okay, the second question I'm going to address today is, for a given star in the universe, in the Milky Way, typically how many planets it has in those neighborhoods? Is it 1 planet, 2 planets, 3 planets, 10 planets, 100 planets? And from our solar system, again, we know there are about 4 planets, the terrestrial planet, in the innermost region. So by 4, I mean, this is about 1 decade inside my major axis. We have 4 of them in this decade. So the average spacing between these 4 planets is, using a dynamical term, is measuring Hill radii, is 30 Hill radii. Okay? So that's the spacing in our solar system. Okay, so jump to the results. What are these planets made of? What I'm plotting here, unlike usual conventions, people plot planet masses versus radius. What I'm plotting here is planet density versus planet radius for those Kepler systems. The yellow points is density. The yellow points here are densities measured by radial velocity work, incredibly painstaking work. Okay, but the green and blue points plotted here are planet densities obtained from TTV work that we've done over the last years. And I should admit, this is a really, really cheap work. Each one of this, getting one of these points takes about 1 microsecond of CPU time. It's not to bloat, but we have much, much huger error bars compared to the radial velocity ones. Okay, but what do we learn from this density plot? First thing is that I also plotted mass of the planets in this slanted curve. Okay, and you can tell this. Sorry, this is too loud. You can tell these Kepler planets typically have 10 Earth masses. Their masses range between 2 to 20 Earth masses, but typical value is 10 Earth mass. And we even give a sort of mass-radius relationship for this kind of systems. But the next thing you can tell is smaller planets are denser, bigger planets lower density. So this was addressed in one of the earlier talk by Leslie Rogers. And third thing you can tell is composition of these planets. The color curve here is theoretical curve by Jonathan Forney on what kind of density a planet should have if it's made of, say, that wonderful substance called water. But if it's perfect rock or perfect iron, those are the kind of density you have. So looking at this plot, let's figure out what these planets are made of. I gave two easy answers first. Those are the purple spots and the orange spots. Those are easy. Right away you know the purple ones have such a low density, they have to be full of hydrogen gas. They have a huge thick envelopes of hydrogen, and the hydrogen mass fractions between, say, a few percent to half the planet mass. Okay. This one's also easy. This is like the Earth, rocky planets. But 90% or 95% of the Kepler planets is actually in here. They have size ranges about 2 Earth radii. And their composition, if you look at this plot, they can have either a simple extrapolation between the two extreme populations, just rock in the middle plus a little bit of hydrogen. Okay, that would be my naive guess for what their compositions are, given the density. Or they can be really exotic. They can be water worlds. So how do we tell by looking at the density plot what they are made of? I gave two pieces of evidence before I say the answer. Many people already know the answer, but for people who don't, I give two pieces of evidence, and then you are left to yourself to figure out what the composition of those 90% of the Kepler planets are. Okay, this is the first piece of evidence. First piece of clue. If we look at all the Kepler planets, so every one of this is everyone that thought is a Kepler planet. If you plot their orbital period versus their size, we can claim that hotter planets are smaller. So there's no planets up here. That's the first. And then same thing that if we plot densities of planets versus periods, distance away from the star, we can claim that hotter planets are denser. So no planets in this neighborhood. Okay, that's the first piece of clue to the composition question. This is my second piece of clue. If I take all the Kepler planets into account, either only take multiple planets or take everybody into account, you plot the size distribution. There's a size distribution. Even to my untrained eyes, it looks like a bimodal distribution. Perhaps only to my untrained eye, it looks like a bimodal distribution. Bimodal in the sense that there's a clump around 1.5 Earth radii, and there's another clump around 2.5 Earth radii. Could this be data analysis problem? Could this be real physics telling us something fundamental? We decided to split this population of Kepler planets by their so-called X-ray exposure. So each planet, after 5 billion years lifetime, receives certain amount of X-ray from their host stars. And we just counted by, whoever received high X-ray exposure, we give a color brown. And if you receive very low X-ray exposure, we give a color blue. Okay? So that bimodal distribution, in this case, split into two groups. Why is that? So this is our interpretation for why there's such a bimodal distribution and why it depends on X-ray like this. Okay? Let's say all the Kepler planets were originally formed at 2.5 Earth radii. Everybody was formed at this size. Every Kepler planet is the same. They all form the same size. But if they receive high X-ray exposure from the host star, what happened to them? They lost that blue layer, which is called hydrogen, and they reduce in size by a factor of 2. They become the brown clump. So that's our interpretation for the composition of these planets. Although they can have any composition, they can be water worlds or they can be rock plus hydrogen. Because of these two pieces of clue, we believe they are rock plus hydrogen planets. And this is sort of a cartoon picture of what we believe have happened. This is a formation. Every planet has a little layer of blue around them. Only about 1% mass in that blue. But because hydrogen is such a low molecular weight, it makes the planet twice as big. But then the ones which are very close to the star receive so much X-rays, photo evaporation was able to rip off those blue layers. They become naked, and that's why the size is reduced by a factor of 2. Okay. What really puzzled us in this study is that by making such a statement, we claim that every planet when they formed, every Kepler planet when they formed, they all have a characteristic mass of 10 Earth mass. And they also have a characteristic hydrogen mass of 1%. What determines those two magic numbers? I wish I know. Okay, so let me go to this. Okay. Okay. All right. Let me relax a bit. So that was a structure question. What's the typical composition of a typical Kepler planet? It's 10 Earth mass plus 1% hydrogen. So I want you to remember this magic number 10. This is going to be a number that comes up again in my talk. So if you don't remember anything from this talk, it's the number 10. Okay, so let me get to the second point, which is how many planets do an average star in the Milky Way host? How many Kepler planets? Okay. And I said before that the solar system have about 4. Oh, so the inflation. Okay. Before I give you the answer, what we found, let me first pose a sort of interesting toy problem, theoretical problem, is how many planets can you pack in? Okay, this is apparently our own, very own Mr. Kepler in 1611 posed the same problem, but for oranges in the crate. He asked for a given crate, what's the maximum packing for oranges? He didn't solve the problem. He posed the problem. It's a famous mathematical problem. But he forgot to pose the same problem for planets, which is more interesting. So we have, let's say we have 10 Earth mass planet in the system. Everybody's circular orbit, no inclination from the midplane. Like Rosemary Martin said, that was the most stable possible configuration. So let's do that, and let's pack planet into such a configuration. How many can we pack? Okay. The answer is number 10. If you maximally pack 10 Earth mass planets around each other, they have to be spaced by at least 10 Hill radii. It's funny, it sounds like a simple answer, but we actually don't understand why that is so. It's an empirical result. Okay? So 10 planets, 10 Hill radii, which means for each logarithmic decade of semi-major axis, you can exactly pack in 10 planets. Okay, let's look at the Kepler system. So here is a plot of spacing of between adjacent pairs in the Kepler system. In the units of Kepler, excuse me, in the units of Hugh radius. This line here is 10 Hugh radii. In here, I'm only using the Kepler system, which I have, high multiples, 4 planets transiting or more. Okay, I'm not using the other group. I'm deliberately not using the bigger group, which is single transiting planet, because you can't do this exercise. Also, I'm not using the double transiting planet, but only high multiples. And you can see they piled up at this 10. In fact, we have evidence to say the ones here, which looks like they're bigger spacing than the 10, those are actually harmonics. They're very big, they're big spacing because we're missing some planet in the middle. So if you take into account of that, the peak here is going to be piled up at 10. So everybody's piled up at 10 Hugh radii. I also marked the spacing of the terrestrial planets. So Rosemary Martin talked about solar system being packed. Well, if you look at the number of Hugh radii, it's actually quite big, quite a bit bigger than the Kepler system. There have been lots and lots of work on why we only have 4 terrestrial planets in the solar system. I list a number of those works, beautiful works. But now, given the packing of the Kepler system, you wonder whether we actually understood the terrestrial systems. This is the spacing for lower multiple, but I'm not going to talk about it. Okay. This was my original talk, but now it's only in 1 slide. The point is that we have double transiting system, triples, quadruple. I couldn't really do the names, but this actually turns out to be different dynamical systems. The higher multiples are distinct. The higher multiples, everybody bigger than 4 and 5 and 6 and 7, they're distinct. They're tightly packed. They're very, very low eccentricity and inclination. We get typical values 1% or less. Okay? Those are the ones I'm talking about. They're very, very tightly packed. But these ones, doubles, singles, and triples, and so on, they contain a large fraction of other type of planetary system. They have high eccentricity and big spacings. This is some of this was my talk, I'm not going to explain it, but for those kind of big spacing, high eccentricity inclination system, we led to believe that this is what happened. This is how planetary systems were made. They were initially all made 10 planets in the system, but then some of those 10 planet systems survived, but a large fraction of them went unstable and become big spacing, lower multiples in the Kepler. Okay, so I explained my number 10 multiple times. This is the conclusion on the Kepler system in terms of their spacing. So individual stars, when they were born, we believe they have 10 planets in that logarithmic decade, about 0.1 AU. Let me just show one last graph. Okay, this is for fun. You're not supposed to take this seriously. Let me just calculate how much mass are in those planets. If I take each planet is 10 Earth mass, okay, that's the first factor of 10. And there are 10 planets per decade, that's the second 10. And let me multiply by a factor of 100, because these planets are mostly rocks. Most of the mass is in rocks, so I need to multiply 100 to get the gas mass. I get 0.03 solar mass, which is 1 minimum mass solar nebula. Just for fun, I did it in my computer. I put in all these numbers I was getting, 10 Earth mass, 10 Hugh radii, and asked what's the Q value. This never happened to me before. Q is 1.0000. No. Okay, that's the end of my talk. Thanks.
Hi. Could you comment a little bit more on, I'm over here. Hi. Could you comment a little bit more on what this implies on the efficiency of planet formation? I guess you imply that it is extremely efficient, and you essentially turn everything into planets. And also, how you think this connects to ice giants, which are in the region of 10 Earth masses, but have a little bit more hydrogen helium in them, I believe.
So the question is, can I comment on the planet formation efficiency? It's high.
Yeah.
And then the second question is,
what about the ice giants further out?
Okay. So we see plenty of Neptunes in this neighborhood in the Kepler database, but they only compose about 10 to 15% of all the planets. So they do occur. There are planets which are able to accrete more than 1% hydrogen mass, like the ones I talk about. There are ones which are able to accrete 50%. Why that is so? I don't know, but I could report that they tend to appear more frequently around higher mass stars. So there's perhaps some mass dependency or disk mass dependency we don't quite understand yet.
One quick question. Yeah, so my question was on your masses. Did you just assume zero eccentricity, or can you say how your results might be sensitive to eccentricities as high as 1%?
Have you not read our paper? You sure?
I have read your paper, but you said there's statistically a good chance of having the systems, statistically they all have low eccentricities, but none of them individually can be shown to have a very low eccentricity.
So the masses here, so I'll make a disclaimer. The mass, TdV mass we determine here are incredibly sensitive to planet eccentricity. 1% of planet eccentricity would change mass by factor 2.
Yeah, but my question is, are your results later on things like the Hill radii and so on,
right,
is that sensitive to
so
uncertainty
the
in mass?
10 Hill radii I was giving for theoretical limits was assuming zero eccentricity, and the question you have is that if eccentricity 0.01, how much tighter can you plug the in? That's a summer project my students doing. It's a good question.